Good day. So today we will be talking about nodal analysis. Specifically in this particular video, we will be showing you how to apply nodal analysis in calculating branch circuit currents, which we typically solve using KCL and KVL. So let's start. Suppose that we have this particular circuit composed of 7-volt source, 6 ohm, 5 ohm, 3 ohm, and 9 ohm resistances, and a 10 amperes current source. And we are asked to solve for the branch circuit currents. Typically, we will be solving this using Kirchhoff's analysis, using KCL and KBL. Since there are 4 unknowns, then we have to have 4 equations. But today we will be using nodal analysis to solve for this. And instead of using 4 equations, we will just be using 2 equations, which is dependent on the number of node voltages. So for our nodal analysis, the first step is for us to identify what we call the reference node or our ground. This is very important because this particular ground will serve as a 0-volt potential point wherein all node voltages will be referred to. So in this case, we will be choosing the bottom node because it is the node with the most element connected to it. The next step is for us to identify the nodes that are non-reference. We have actually 3 here. We have the node that connects the 7-volt and the 6 ohm resistance. We have another node that connects the 6, 5, and the 3 ohm resistances. And we have the last node that connects the 5 ohm, the 9 ohm resistances, and the 10 ampere current source. However, in this particular solution, we will be only considering the one with at least 3 elements connected to it. That is the VA and the BB. We have not considered the node between the 7-volt and the 6 ohm because we can readily solve that by considering the 7-volt source being connected to it and the ground. Therefore, that particular node has a 7-volt potential. Now that we have identified our non-reference node, we have seen that we have 2 variables here, the VA and the VB. Therefore, we will be needing 2 equations. How do we get that equation? First is to apply KCL on node A. If we will look at the node A, we can see that we have 3 currents here. We have the I1, the I2, and the I3. And since I1 is entering, then we can say that it is positive, and I2 and I3 are leaving, so they are both negative. And we can say that the equation is I1 minus I2 minus I3 equals 0. So the next step is for us to express our branch circuit current in terms of the node voltages. So for I1, we can observe that it is flowing from the 7-volt source to VA. Applying the principle of that the current flows from higher potential to lower potential, then we can say that the voltage drop at the 6 ohm resistance is the 7 volts minus the VA. So therefore, I1 can be expressed at 7 minus VA all over the resistance, which is 6. Similarly, I2 can be observed that it flows from VA to the reference node. So we can express that as higher potential being VA. So VA minus 0 all over 3. 0 because it flows to the reference node. And then I3 is flowing from the VA to the VB. So therefore, we can say that VA minus VB over 5 is equal to 0. So now that we have this particular equation, we can use algebra to simplify this. So we just have to use the LCD, in this case 30. So we'll multiply that to express, to simplify this particular equation. Now we have 35 minus 5VA minus 10VA minus 6VA plus 6BB equals 0. Combining similar terms and rearranging the equation, we have 21VA minus 6BB equals 35. This will be our equation number 1. Now let us proceed to our equation number 2. We will be applying KCL at node B. So we have I3 because I3 is flowing, so we have positive. We have I4 leaving, so we have negative I4. And we also have the 10 ampere current source entering the node B, so we have plus 10 equals 0. Then we will also express I3, I4 in terms of our node voltages. So I3 is VA minus VB over 5. I4 is VB minus 0 over 9. And then plus 10 equals 0. So the LCD here is 45. 45 times VA over 5 is 9VA. Then we have also negative 9VB minus 5VB plus 450 equals 0. Rearranging and simplifying the equation, we have 9VA minus 14BB equals negative 450. This is our equation number 2. Now that we have two equations, we can now simply solve for the VA and BB using methods of elimination and substitution. We can see that we can solve for BB is equals to 1085 over 80 over 3, or BB is equals to 40.6875. By substituting the value of BB to equation number 2, we can solve for VA. VA is 13.2917 volts. Now that we have VA and VB, we can go back to our required branch circuit current and solve for the individual branch circuit current in terms of using the values of VA and VB. So we have I1 is simply equal to 7 minus VA over 6. Substituting the value of VA, then we can solve for I1 is equal to negative 1.0486 amperes. The negative value of I1 means that the cleared direction of the current is opposite to the actual direction of the current for I1. So similarly, for I2, we can solve for that. So substitute the value, and then we have 4.4306. I3 is negative 5.4792 amperes, and then I4 is equal to 4.45208 amperes. If you still doubt your answer, you can simply substitute back your I1, I2, I3, and I4 to our KCL equations and check whether your answers are correct. So that is the process of using nodal analysis to solve for our branch circuit currents. So it is quite simple. Let us review that. Number one, we have to identify our reference node or our ground. The next one is to identify our non-reference node. In this case, we have VA and VB. Then we apply KCL to that non-reference nodes. Then express your branch circuit currents in terms of your node voltages. And use algebra to solve for the node voltages using the method of elimination, substitution. You can also use Kramer's rule or Gauss-Jordan method. So once you have solved your node voltages, then you can now solve for your branch circuit current by simply substituting back the node voltages to the equation for your I1, I2, I3, and I4. So that's it, and God bless.